You type shoes that look like clouds into a search bar. Traditional databases would panic. There's no column called cloud likeness. But somehow you get exactly what you wanted. That's embeddings and vector databases working together. And if you're building anything with AI right now, search, recommendations, chatbots, RAG applications, these two concepts are the foundation. In this video, we'll look at both of these and hopefully get a better understanding. Databases are incredible at exact matches. Show me all red shoes under $50. Done. The query maps perfectly to columns. But there's a problem. Comfortable, standing all day, concert. Where's the column for that? Traditional databases store data, but humans communicate in meaning, and meaning doesn't fit in rows and columns. We needed a way to capture meaning itself, mathematically. A way to make computers understand that puppy and dog are related even though they share no letters. Enter embeddings. An embedding is this. Take any piece of data, a word, a sentence, an image, and convert it into a list of numbers. That's it. But these aren't random numbers. They're coordinates, a position in space. Imagine a simple 2D space. We plot king somewhere. Now let's add more words. King and queen end up close together. Apple and banana cluster together. King and banana, far apart. Embeddings capture meaning as distance. Similar concepts become nearby points. Now, how do we go from 2 dimensions to the 1,500 that real models use? Imagine describing movies with 2 traits, how funny it is and how scary. Comedies here, horror here, horror comedies like Shaun of the Dead in between. But 2 traits can't capture everything. Is it romantic? Animated? A sequel? Set in space? Each trait is a dimension. 1,500 dimensions means the model captures 1,500 different aspects of meaning. Things like, is this formal or casual? Positive or negative? Technical or conversational? A question or a statement? Abstract or concrete? We don't program these. The model discovers them from patterns in billions of examples. And while we can't visualize 1,500 dimensions, the math works identically. Similar things remain nearby points. 1,500 invisible traits, but do they actually capture meaning? King minus man plus woman equals queen. Arithmetic on meaning. When researchers at Google demonstrated this consistently in 2013, it proved embeddings capture real semantic structure, not just surface patterns. Remember our shoe search? Shoes that look like clouds becomes a vector that lands near cushioned sneakers, pillowy foam runners, soft-sole trainers, because the embedding captures the feeling you're describing. Where do these meaningful numbers come from? A neural network trained on a deceptively simple task. The model sees billions of sentences with a word hidden. Its job? Predict what's missing. To predict well, it must understand what cats do, what sitting means, what surfaces exist. That understanding, learned from patterns across billions of examples, gets compressed into the network's internal state. We extract that internal state. That's your embedding, the model's learned intuition frozen into numbers. Today, you rarely train these yourself. You call an API, a few lines to convert language into mathematical coordinates. Now you have millions of these. How do you search them without comparing every single one? This is exactly what vector databases were built for. The challenge is simple to state, brutal to solve. You have a query embedding, a million stored embeddings, find the most similar ones. The brute force approach, calculate the distance between your query and every single vector. For 1,136 dimension vectors, that's over 1.5 billion calculations per query. Vector databases solve this with intelligent indexing. They don't compare against everything, they dramatically narrow the search space.
Instead of searching an entire library book by book, you go to the right section, then the right shelf, then scan just the nearby books. Section, shelf, scan. That's the principle. Now let's see how vector databases actually pull it off. Vector databases combine three core ideas. First, distance metrics. How do we define similar? The most common is cosine similarity, measuring the angle between vectors. Same direction, score of 1. Perpendicular, 0. Opposite, -1. There's also Euclidean distance, straight line distance between the arrow tips. Cosine similarity is the default for text, Euclidean common for images. Most databases support both. Second, indexing. This is where the performance magic happens. One popular algorithm is HNSW, Hierarchical Navigable Small World. The name actually explains how it works. Small world comes from 6 degrees of separation. In social networks, any two strangers connect through surprisingly few mutual friends. HNSW builds the same structure for vectors. The insight, it builds the graph in layers, and that's what makes it fast. Why does this help? Imagine navigating with only local connections. You'd take hundreds of tiny hops just to cross the space. The top layer fixes that. Long-range connections let you skip most of the distance in a few jumps. Then you drop down for precision. Think GPS navigation. Top layer is highways, long-distance jumps to the right region. Bottom layer is local streets, small, precise moves. Parks right next to its nearest neighbors. Instead of a million distance calculations, a few hundred. Milliseconds instead of seconds. One trade-off to know. This is approximate nearest neighbors. HNSW might occasionally miss the absolute closest vector, but it finds very good neighbors very fast. For search, recommendations, and RAG, that trade-off is almost always worth it. Third, filtered search. Real applications don't just need most similar, they need most similar where category equals footwear and price under 100. Strong vector databases combine similarity search with metadata filters in a single efficient query. One common mistake, never mix embeddings from different models. A vector from OpenAI and a vector from Google exist in completely different mathematical spaces. Comparing them is meaningless. It's like mixing Celsius and Fahrenheit. Same number, completely different meaning. Always embed your queries with the exact same model you used for your stored data. Let's see what you'll actually build with this. Semantic search. User types reduce cloud costs. Your system returns documents about AWS spend optimization and infrastructure budgeting, even though those exact words weren't in the query. The embedding understood the intent, not just the keywords. Retrieval Augmented Generation, or RAG, the backbone of AI assistants that actually know your data. Embed your documentation, store the vectors. When users ask questions, retrieve the relevant chunks, pass them to an LLM as context. Instant expert on your content. Recommendations. Embed products by their descriptions and attributes. Embed user behavior as preference vectors. Find where they overlap. Multimodal search. Models like Clip embed images and text into the same vector space. Search your photo library with natural language. Beach sunset with the dog finds the right memories. No manual tagging required. Let's lock in the complete mental model. Raw data comes in, text, images, audio, whatever you're working with. An embedding model converts it to vectors, numerical coordinates that capture meaning in high-dimensional space. A vector database stores those vectors in intelligent index structures designed for fast similarity retrieval. Queries get embedded with the same model. The database finds similar vectors in milliseconds, not minutes. Your application uses those results for search, RAG, recommendations, whatever you're building. Embeddings turn meaning into geometry. Vector databases make that geometry searchable at scale. Together, a core building block for AI-powered applications.
That search for cloud-like shoes, now you know exactly what's happening under the hood. The query becomes a vector. The vector finds its neighbors. The neighbors are your results. Meaning captured as math. searchable at scale. And this is how it works. If this helps, please like and share. Thanks for watching, and see you in the next one.